Okay, and thank you for the kind introduction, and welcome everyone. So we at Nvidia we started a new applied research team looking into solutions for medical imaging, mainly in the deep learning space. So I joined this team about 6 months ago, and today I want to talk a little bit about how Nvidia can help you as researchers and people who want to apply deep learning technology in the healthcare applications, how we can help you to tackle the next challenges for the next generation of healthcare. Okay, so at Nvidia we realized that medical imaging is a difficult computational problem, which GPUs have been applied to for over 10 years already. And as I think all of you will agree, is that as we move forward, we will see more and more computational demands in this sector. So if you look a little bit at the history of Nvidia's involvement in healthcare, it really kind of started in 2007 with the release of CUDA. And then you would, shortly after that, you would see this being applied in real-world applications like speeding up the rendering for 3D ultrasound, then also in the genomics field. And then around 2012, when you would say the deep learning kind of revolution started with Alex Krizhevsky's paper on ImageNet, it took a while for these methods to be applied in medical imaging, but around 2014 we would see the first successful application of brain tumor segmentation using deep learning approaches. And 2016 is roughly, I think you could see the first commercial applications that use the deep learning methods, for example, for detecting lung cancer. So now, only in March 2018, Nvidia announced a new product line that's providing dedicated solutions for the healthcare sector called Project Clara. And I will be talking about that a little bit more. So, as you all know, computation in imaging is everywhere. So this morning we heard a lot about using it in reconstruction. Then for advanced visualization, we need more and more compute. So the new thing is cinematic rendering, which basically generates very realistic looking 3D visualizations from things like CT data. But a big focus, of course, is also the analysis and planning, where you need more and more compute for applying deep learning for computer-aided diagnosis and radiotherapy planning or image-based quantifications. And only last week, the largest radiology conference in the world happened in Chicago, RSNA. And you could really see that this AI is now at an inflection point in radiology. So last year, 2017, there was still a lot of questioning if AI is going to make it into radiology. I think that this year, everyone was agreeing that it's going to come. It's more the question of how it's going to be implemented. So if you look at things like in the academic field, we see like an exponential growth of publications using deep learning. At one of the major medical imaging conferences, MICAI, we had like 70% of the papers now using deep learning. There are more and more startups around this topic with over $4 billion in investment. And of course, the big imaging vendors are also developing hundreds of AI applications for their field of expertise. And we see in the clinical institutions, we see more and more dedicated centers to develop AI applications, like the Center for Clinical Data Science, just to mention one. So AI is transforming radiology. In the past, techniques like reconstruction and image processing would use classical methods, but we can see that in all these different workflows, from the acquisition to quality assurance and image processing, the work list scheduling, interpretation, and reporting is all fields where we will see artificial intelligence or machine learning which will play a role. So for the last few years, Nvidia was thinking hard about how they can speed up or accelerate the path to clinical grade AI. So in 2017, we announced the Nvidia DGX systems, which are basically hardware solutions for your data center or the cloud. And NGC would be the Nvidia GPU cloud AI registry, which provides you with dedicated Docker containers for AI solutions. And then for radiology, we provided last year at RSNA over 1,000 courses from the Deep Learning Institute to teach or to train radiologists the basics about machine learning and how it can be beneficial for their field. So that's on the research and development side. And then for integration and deployment, we announced the Nvidia Tensor RT, which basically you can use a model trained with your favorite framework and then optimize it to the targeted hardware that you will be using to deploy your models. One of the feedback we got back is basically mainly from researchers on the development side is we need more labeled data, and we need easier and faster ways to train. And for the deployment, we need more easy ways to deploy models and AI applications. So last week, we kind of announced two things that can help with solving this problem. So on the research and the development side, we have the AI-assisted annotation SDK and a transfer toolkit for specializing for medical imaging. So I will be talking more about that. And on the deployment side, the Nvidia Clara SDK now provides dedicated AI inference engines and Tensor RT inference server, together with some rendering server and a web user interface to show all the processes running. So again, these are two new development tools for radiologists, but also for people developing new methods. Also, one of the big challenges, of course, for medical imaging is just the computational demands. So also on the I/O sensor reading side, we have a demand for high-speed sensor processing, up to 1,000 gigabit per second, and then high compute for things like reconstruction, AI and image processing and visualization. So the Clara platform is also bringing you some dedicated embedded devices, which basically can be installed on the instrument side of things. So for many of the real-time applications, you want to have to compute directly where the sensor or where the data is acquired. And then for things that run on the cloud, we will provide the Clara SDK. So there are already thousands of, there's already a set of dedicated developers who use the Clara SDK with thousands of instrument applications. So currently there are two different versions of this embedded systems. They're based on the Xavier platform, which basically has been developed for autonomous driving. So making use of all the sensors coming in on a camera and radar in the car. But we can use a very similar architecture to dedicate or to speed up AI applications for the medical instruments. And then again, the Clara SDK has some specific libraries targeting the medical imaging. It's compatible with raw and DICOM data and supports standalone apps and microservices. And it makes use of Nvidia's optimized Docker containers in Kubernetes for scalability and provides a set of accelerated libraries. So if you're interested, please have a look at this link, and you can find out much more information about that. So I want to talk also a little bit more about the computational challenges in medical imaging. So one field that's growing is digital pathology, and there we have the challenge that the images are just very large. So, for example, a full 4K ultra high definition resolution would only cover a small patch of a whole slide histology image. But then you have the problem that abnormalities can also be sometimes only very tiny islands. So approaches that would maybe downsample the resolution of this image are not desirable because you will lose your ability to find the abnormalities. So in order to speed processing these kind of images up, we can make use of a V100 Tensor Core GPU, for example. And for inference, we would basically tile these images up in small patches, where each patch then can be processed in parallel on several GPUs. And then you get this kind of factor 4 speed up if you run it on 4 GPUs. And I just want to mention here that we also announced, also provided DGX2, which actually has 512 gigabyte of unified memory. So here you could actually process an entire whole slide image in one go. But this is really a targeted solution for your data center. Okay, so now I want to move a little bit more towards what we're doing in the applied research field. And there have been a couple of highlights this year for AI in medical imaging. For example, we use generated adversarial networks to generate abnormal brain MRI. I will be talking about this a little bit more. Then we also have the brain tumor segmentation, where we won the challenge this year. And this is the medical image segmentation decathlon, where we achieved one of the top performance segmentation performances. This is a learning reconstruction from undersampled MRI scans. This comes from Nvidia research in Helsinki. I think we heard a lot about this this morning, so I'll skip this. So for the brain tumor segmentation, this challenge has been running for a few years now at MICAI. And the organizers provide you with multi-parametric isotropic MRI scans with isotropic resolution. Sorry, this is automated. So we have T1, T1 with contrast, where you can see the tumor core, and T2, where you can see more of the whole tumor. And these 4 parametric scans have kind of 240 times 240 by 155. And we're basically training a fully convolutional model to segment these with there are 285 images for training, and there's a validation set provided, and then the final test set that's used to determine the winner of the challenge. Okay, and the network we came up with is something based on a encoder-decoder structure, so basically a 3D unit. What is interesting here is that we are able to use NVIDIA's 32 gigabyte graphics cards to feed in the entire image, multi-parametric image into the network. And so everything is processed in one go. And we found that this actually helped in terms of the segmentation performance when you compare to like a sliding window approach. Then one of the novelties here is that instead of just doing the segmentation branch here, we also added a variational autoencoder branch that allows us to reconstruct the image. So this is acting as a type of self-regularization and helps this kind of encoder to learn better features that are more robust to unseen data. And we achieve about 1% to 2% better average dice in testing, which in this kind of data set where a lot of people are working on it, 1% to 2% is quite significant. And it helped us to win the challenge. So for training these kind of networks, we are kind of lucky that we have a large GPU cluster available, the DGX Saturn V. So these are DGX1 servers with up to 8 GPUs. And we can basically see if we would use one GPU with 32 gigabyte to train this model, takes about 2 days on the 285 training cases. And by making use of 8 GPUs, we can get it down to 6 hours. So that kind of speed up allows you, of course, to navigate a much larger model space in terms of for architecture search and hyperparameter tuning. So by doing this, we were able to test a lot of different variations of the 3D unit and achieve the winning performance. So then here you can see this integrated in one of our Clara SDK partners. This is Infusion from Germany. We integrated the model into the viewer to kind of visualize how this looks in 3D. Okay, so the next part is about the generative adversarial networks. And we are thinking of ways to make it easier for people to work on medical imaging problems where getting data is very difficult. One thing is the annotation is very time consuming and expensive because you typically need an expert to do annotations. And because of ethical or privacy reasons, it's difficult to share data sets across institutions. So what we can do is that we can train a generative adversarial network to synthesize new brain images. This can then act as a way of data augmentation. You know, the classical data augmentation like zooming and translations or even elastic deformations only adds so much new information to the images. There's still a lot of redundant information, like the tumor here is on the same location. So by using a GAN, we can actually synthesize new images. And we can also formulate this as a conditional GAN to randomly place more tumors into healthy brain images. So this would be a healthy image. And we can vary the size and locations of the tumors. And so basically generate more images that have abnormalities, which are in the real data set, they're typically underrepresented by a smaller percentage. Okay, and I should also mention that then you can also think about training these models on a private data set, maybe at one institution, and then instead of having to share the data for other people to use, you can share this model and then generate new data, basically where other institutions could base their models on. And we show that by doing this, you can actually get a better performance for things like lesion segmentation in the brain. So this is in the workshop paper here. Okay, so another way of dealing with the limited data that we have in medical imaging is to think about ways of making use of unlabeled data. So this is some work by one of our summer interns who spent 3 months as an internship in our team. And he basically came up with a way of formulating a 3D image as a multi-view problem. And you can basically think of the 3D volume as having a different principal directions, and we can sample we can have a network that is basically processing the 3D volume from different views. There we make use of a network that was proposed by or pioneered by some researchers from Siemens Medical Research, where you would basically it's using a ResNet architecture in the encoder path, but we use anisotropic filters, which then have the advantage that they can be pre-trained with weights from natural images like ImageNet. And by applying them in so these anisotropic filter kernels would still be applied in the full 3D volume in like a 3D convolutional fashion, but looking at different directions of the volume. So then each of these networks can provide you with a pseudo-label on the unlabeled data that we can use to train the corresponding view from a different direction. So this is kind of a co-training approach. And by doing so, we can learn complementary data to constrain images with only a few, to constrain the models with only a few labeled images, but with a larger set of unlabeled images. So if we look at this here, I think we use about 20 images to train the different views, only using the labeled data, and you can see that the models are making a lot of false positive predictions here. This is for the pancreas. But if we use our method for training unlabeled data, we can actually get much more consistent segmentations. And by using these different views predictions in a kind of ensemble fashion, we also get some uncertainty measures from that, and we get a pretty good performance overall. Okay, so for the next part, I want to talk a little bit more about what we worked on to help basically the transition of deep learning methods into clinical practice. So one thing is the Nvidia transfer learning toolkit and the annotation toolkit. So that will be released for early access in January. So I think we heard about this earlier as well, is that we know that the deep learning models are sensitive to domain changes, and between clinical institutions, you can have variations in the acquisition protocols, or the equipment can change. Also, if you start looking at the worldwide scale, you will see patient populations and demographics change. So one way to compensate this is via transfer learning. So we can use a fewer amount of images from the target domain and adapt our models there. So we want to provide an opportunity to use state-of-the-art deep learning techniques in specific domains. And the way we envision this is basically like this. The Nvidia will provide a set of pre-trained models for different common medical imaging applications. We will provide this as an initial model, and then the user can use also our annotation tools to provide some labeled examples on their data and refine the model. And this is kind of formulated in an active learning framework, so that this is a loop with the human in the loop, and we end up with a refined model. So for example, on the brain tumor segmentation, we do have our internal pre-trained Nvidia model that works well on a public data set. But of course, when we try it on a partner data set, the performance will go down. Then on the other hand, a lot of the larger clinical institutions have their own deep learning models already developed, but they might not quite employing the latest architectures from the state of the art. So they have a better performance on their own data, but they underperform on the public data set. So by using the transfer learning toolkit, we can, first of all, improve our model as well on the public data, but also get a better performance on the targeted domain. So after retraining and fine-tuning, we are using our transfer learning toolkit. The accuracy will be better. And overall, this can accelerate the time to production-ready models, which then could be employed with using the Clara SDK inference server, for example. So, this is kind of a general, that was a general purpose medical imaging training tool. So the transfer learning toolkit also allows you to train from scratch, of course. But in order to really implement this in practice, we also want to provide some tools for speeding up the annotation process itself. And as we heard from Olaf earlier this morning, annotation is important for radiotherapy planning or surgical interventions, or to generate training data for deep learning. But radiologists can spend hours sometimes on a single case. And at the large centers, we sometimes have thousands of cases that need to be annotated on a single day. So here I showed an example from MITK Workbench, which is an open source medical imaging viewer. And if the user uses some of the standard tools for annotating on a slice-by-slice basis, it just it's very tedious, error-prone, and takes a lot of time. There are some more dedicated commercial tools that can speed up this annotation process, but it's still quite time-consuming. So what we provide here is a microservice that can basically run in the background and allows the user to only define a rough set of 3D points around the targeted organ. And then based on that region of interest, we provide a segmentation mask. Then we also provide some tools for doing assisted correction. So here the mask is then converted to a polygon representation, and the user can modify that polygon to correct the segmentation. And the way this works is that we only, let's say the mask is missing some part of the liver here, then the user would only need to track one polygon, and the neighborhood of the polygon, neighborhood mask is being updated. And again, what we see here is that the speed up is kind of, the speed up you get from the AI assisted annotation is up to 10 times. And it's kind of depending on different data sets, like things like the liver are very large, so they take longer to annotate. Spleen is typically a little bit easier from the shape, but things like the pancreas is, you need a lot of expert knowledge basically to find the boundary, so it takes longer. But by using our annotation tools, we can speed up this process. So this AI-assisted annotation is will be provided as a SDK together with the transfer learning toolkit, and we deploy this as a optimized container on the NGC registry. And it includes the assisted annotation, which only takes the approximate points as input and returns auto-annotated results. The polygon editing, which can reduce the time it takes to correct the initial segmentation, and the transfer learning toolkit allows you to refine your models. And then again, overall, this is kind of envisioned as a loop where the user starts annotating more and more cases, and at some point we can get enough accuracies from the model that we can fully automatically segment new cases. And then, of course, we're also working on ways of estimating uncertainty in these models, so we can flag images that are more likely to need some correction from the user. So because we developed everything as a microservice, so that the annotation assistant can actually run somewhere on your data center or in the cloud, we can easily integrate with other imaging vendors or imaging tools. So here, this is an in-house viewer from the Center for Clinical Data Science at MGH, and they were able in about a week to integrate our server with their annotation tool and then get the initial polygons returned. So we demoed this at RSNA last week and got a lot of feedback, positive feedback back from radiologists and developers. So please, if you're interested, have a look here at this link, and you can sign up for our early access partnership, and hopefully you can provide us with more feedback. So finally, I just want to mention again kind of useful tools that Nvidia provides, maybe for you as developers. So the Tensor RT version 5 has just been announced a few weeks ago, I think. And the new parts are basically this containerized inference server engine, Docker and Kubernetes integration, has a new set of layers and APIs, I think, for things like model pruning, for example, and extended supports for OS. So again, this allows you to basically calibrate your model that's been trained on one of these popular frameworks towards your targeted hardware, so you can actually get speed ups in inference or get more memory efficient models. And then this also comes with the Tensor RT inference server, which allows you to easier deploy over multiple GPUs, has support for all the AI frameworks, both GPU and CPU. And there's like an integrated scheduling system in there, which allows you to maximize your GPU utilization. Again, using the Docker containers that we provide, it's kind of easier to deploy on a new environment. All these containers are ready to run and downloadable from the container registry. Okay, so then another thing I'd like to mention, this is not from the applied research team, but from Nvidia in more general. It's something we announced a couple of weeks ago. It's the RabbitM, which is built on more than 15 years of Nvidia CUDA development and machine learning expertise. It's a powerful new software for executing end-to-end data science training pipelines completely in the GPU. So by doing a lot of these data science computations on the GPU, we are able to reduce the compute drastically compared to using a CPU cluster. And a lot of the things actually that they have partnered with Apache Sparks, I think, to speed up the data loading procedures very drastically. So this blue bars have been reduced a lot. Okay, so to summarize, this is basically summarizing NVIDIA's AI platform for the healthcare sector. So we have dedicated GPUs with large memory, 32 gigabyte, and we have the DGX systems that basically allow you to employ this in your data center. We have the optimized Docker containers and Rapids for easy integration of machine learning. Then for people who are maybe a little bit new to the field, we also provide a deep learning institute courses, which are a great way of learning about new technology coming from Nvidia or machine learning in general. Nvidia Digits is a web-based interface which allows you to do rapid prototyping of deep learning models. And then really dedicated for the healthcare sector, we have the transfer learning toolkit and the annotation assistant server together integrated with Tensor RT and the project Clara. So with that, I would like to thank you for your attention. And if you're interested in doing internships or for opportunities within NVIDIA, please drop me an email. Thank you.